Hello everyone, and welcome to a deep dive tutorial on a truly fascinating and powerful corner of the neural network universe, echo state networks. If you've worked with recurrent neural networks like LSTMs or GRUs, you know how powerful they are, but you also know that training them can be incredibly slow and computationally expensive. Today we're going to explore an alternative paradigm called reservoir computing, and specifically its most popular implementation, the Echo State Network or ESN. We're going to learn the theory behind why these networks are so efficient, and then we're going to build one from absolute scratch. But we won't stop there. We'll build an advanced multi-scale ESN and use it as the brain for a reinforcement learning agent tasked with solving the classic CartPole problem. This is a university-level topic, but we're going to break it down step by step so that every component is crystal clear. This will be a long and detailed session, so get comfortable and let's begin our deep dive. You can find the complete project code on our GitHub. Just click the link in the description below this video. Before we dive into our solution, the Echo State Network, let's first understand the problem it was designed to solve. Why do we need an alternative to standard recurrent neural networks like LSTMs or GRUs? While these traditional RNNs are incredibly powerful for processing sequential data, they come with some significant challenges, especially during training. The main training algorithm, backpropagation through time, involves unrolling the network through its history, which is a very slow and memory-hungry process. Furthermore, they suffer from the infamous vanishing and exploding gradients problem. Imagine you're trying to teach the network by sending an error signal backwards in time. As this signal travels, it's repeatedly multiplied by the network's weights. If those weights are small, the signal can shrink exponentially until it vanishes, and the network can't learn from events that happened long ago. If the weights are large, the signal can explode, destabilizing the entire training process. This leads to a difficult and often frustrating process of hyperparameter tuning to get them to work well. This begs the question that researchers asked in the early 2000s: can we get all the benefits of these rich recurrent dynamics without paying the high price of this complex training? The answer, it turns out, is yes. This brings us to the beautiful and elegant core idea of the Echo State Network. The key insight is to decouple the part of the network that creates rich dynamics from the part that actually learns. An ESN consists of three distinct parts. We have an input layer, which simply feeds our external signal into the system. Then we have the heart of the ESN, the reservoir. This is a large, recurrently connected network of neurons. But here's the radical idea. We initialize this reservoir with random weights, and then we freeze it. We never ever train or update these internal connections. Its sole purpose is to act as a high-dimensional, nonlinear echo chamber. When an input signal enters, it causes complex reverberations or echoes throughout this reservoir. The state of the reservoir at any moment is a rich, dynamic reflection of the recent history of the inputs it has seen. Finally, we have the readout layer. This is a very simple linear layer, and it's the only part of the entire system that we train. Its job is to look at the incredibly complex and high-dimensional state of the reservoir's neurons and learn to map that state to our desired output. The best analogy is to imagine throwing a stone, which is our input, into a pond, which is our reservoir. The pond's physics are fixed. You don't train the water. But by observing the complex pattern of ripples on the surface, you can learn to infer what kind of stone was thrown and when. In an ESN, we don't train the reservoir. We only train the readout layer to learn how to interpret the ripples. Before we dive into the code for a single Echo State network, let's first understand the powerful, high-level architecture we'll be using in this project. The multi-scale echo state network. So why would we need more than one reservoir? Think about how you perceive the world. To make a good decision, you need to process information at different speeds or timescales. For the CartPole problem, the agent needs to react to very fast changes, like a sudden wobble of the pole. But it also needs to be aware of slower moving trends, like the cart consistently drifting too far to one side of the track. A single reservoir might be good at one of these, but not the other. A multi-scale ESN solves this by creating a team of specialists. Instead of one giant reservoir, we create several smaller independent reservoirs. Each reservoir in our team is configured with different properties, allowing it to specialize in capturing dynamics at a specific timescale. Let's look at the parameters we'll use in our code to define this team. First, reservoir dimensions. We are creating 3 reservoirs and we are giving them different sizes, 300, 400, and 500 neurons. Giving them different sizes can provide varying levels of complexity and capacity for the patterns they can represent. Next, spectral radii and sparsities. For this particular experiment, we're keeping these consistent across all 3 reservoirs to isolate the effect of the other parameters. They are all set to stable, well-established values. Now, for the most important parameter in our multi-scale design, leaky rates. This is how we create our specialists. We're giving each reservoir a different leaky rate, 0.2, 0.3, and 0.4. The reservoir with a high leaky rate of 0.4 will be our short-term memory expert. Its internal state will be heavily influenced by the most recent input, making it highly reactive and great at capturing fast-changing details. The reservoir with a low leaky rate will be our long-term strategist. Its neurons are more stubborn. They hold on to their previous state more strongly. This allows it to smooth out noisy inputs and integrate information over a much longer period, helping it recognize slow-moving trends. The one in the middle, at 0.3, provides a balanced perspective. The final step is to take the rich state vectors from all 3 of these specialist reservoirs and simply concatenate them together into one large superstate vector. This combined vector is then fed to our single, trainable readout layer. By doing this, we are giving our decision maker the richest possible view of the world. It gets to hear from the short-term specialist, the long-term strategist, and the balanced expert all at once before making its final move. All right, let's dive into the code and build our EchoState network class piece by piece. We'll start with the constructor, the init method. The first thing we do after calling super.init and storing some hyperparameters is to create our input weights, which we'll call win. This is the first component from our diagram. Its job is to take the input vector, which for CartPole has a dimension of 4, and project it into the much higher dimensional space of our reservoir, which might have 300, 400, or 500 neurons. We initialize this weight matrix with random values drawn from a uniform distribution. The torch.rand gives us values between 0 and 1, subtracting 0.5 centers them around 0, and multiplying by 2 scales them to be between -1 and 1. This is a standard way to create initial random weights. Now notice this line, self-register buffer. This is very important. In PyTorch, a parameter is a tensor that the optimizer knows it needs to update during training. A buffer, on the other hand, is a tensor that is part of the model state, but is not considered a trainable parameter. By registering win as a buffer, we are telling PyTorch, this is part of my model, so please move it to the GPU along with everything else, but do not try to calculate gradients for it. This is central to the ESN philosophy of keeping the input and reservoir connections fixed. Okay, we have our input weights. Now for the most interesting part, creating the recurrent reservoir weights, W. This matrix defines how the neurons inside our reservoir are connected to each other. The first step is to introduce sparsity. Why do we do this? A fully connected recurrent network can sometimes have dynamics that are too rigid or chaotic. By making the network sparse, meaning most neurons are not connected to most other neurons, we can encourage richer and more stable patterns to form. It's like having many smaller independent pathways for information to flow and interact. So, how do we do it in code? It's a simple three-step process. First, we create a dense square matrix W of the desired reservoir size with random values centered around 0. Second, we create a Boolean mask of the exact same size. We generate another matrix of random numbers between 0 and 1, and we check where these numbers are greater than our sparsity hyperparameter. So if sparsity is 0.5, this mask will be true for roughly half of its elements. Third, we use this mask to index into our weight matrix W and set those elements to 0. We've effectively just pruned a huge number of connections, leaving us with a sparse, random, recurrent network. The next crucial step is to make sure this network is stable. This next piece of code is the most mathematically important part of creating our ESN. It's called spectral radius scaling, and its job is to ensure our reservoir has the echo state property. In simple terms, this property means that the influence of a past input should gradually fade away over time, but not too quickly. If the echoes die too fast, the network has no memory. If the echoes explode and become chaotic, the network state is useless. We need to find that perfect balance. The key to this balance is the spectral radius of our weight matrix W, which is defined as its largest absolute eigenvalue. For a stable system, this value needs to be less than 1. So our goal is to take our random sparse matrix W and scale it down so that its spectral radius is exactly equal to our desired value spectral radius hyperparameter, which is typically a value like 0.9. Calculating the exact eigenvalues is slow, so instead we use a fast and effective approximation method called power iteration. We start with a random vector EIG. Then we repeatedly multiply our matrix W by this vector. At each step, the vector EIG gets more and more aligned with the principal eigenvector of W. We normalize it at each step to prevent its magnitude from exploding. After about 50 iterations, the norm or length of this vector becomes a very good approximation of the largest eigenvalue. Once we have this maxig, the final step is simple. We just scale our entire weight matrix W by our target spectral radius divided by the max EIG we just found. This guarantees that our new scale W has exactly the spectral radius we want, ensuring our reservoir is stable and ready to produce useful echoes. We then register this final W as a buffer. Now that we've meticulously constructed our ESN in the init method, let's look at the forward pass. This is what happens at every single time step of the simulation. First, we make sure our input x is a flat vector. Then we come to the single most important equation in our network, the state update equation. This is what makes it a leaky integrating ESN. Let's break it down. The torch.tanh part is the standard RNN update. We take the current input x multiplied by the input weights, add it to the previous reservoir state, multiplied by the recurrent weights, and pass it through a tanh activation. This gives us the new potential state, but we don't just replace the old state with the new one. Instead, we perform a weighted average. We take 1 minus leaky rate times the old state, and add leaky rate times the new potential state. The leaky rate is a hyperparameter that controls how fast the reservoir state changes. A small leaky rate means the neurons are stubborn and hold on to their old state for longer, giving the network a longer memory. A large leaky rate makes the neurons update more quickly in response to new inputs. Finally, we normalize the resulting state vector by its norm. This is an extra trick to ensure the activations don't grow too large over time, which further improves the stability of our system. The output of this module is not a prediction, but the rich, high-dimensional state of the reservoir itself. Now, let's see how simple the code for the multi-scale ESN is now that we've done all the hard work in our base EcoState network class. This multi-scale ESN class is essentially a manager for our team of reservoirs. In the init method, instead of single hyperparameters, it takes lists. A list of reservoir, DIMs, spectral, radii, sparsities, and leaky rates. It then uses a list comprehension to create multiple EcoState network instances, one for each set of parameters, and stores them in an NN module list. Then it creates our single trainable readout layer. Notice its input size, sum of reservoir dimensions. If we have reservoirs of size 300, 400, and 500, the input to this readout layer will be 1200. It's going to see the combined state of every reservoir simultaneously. The forward pass is just as elegant. It passes the input X to each reservoir in the list, collecting their individual state vectors. It then uses torch cat to concatenate these state vectors into one single large superstates vector. This combined vector, which contains information at multiple timescales, is then passed to our trainable readout layer to produce the final output scores. With our complex multi-scale ESN brain fully designed, the rest of the setup is standard reinforcement learning practice. First, we have the policy network class. This is an extremely simple but necessary wrapper. Its only job is to take the raw output scores or logits from our ESN and pass them through a softmax function. This converts the scores into a valid probability distribution where each value is between 0 and 1 and they all sum to 1. This gives us the probability of taking each possible action. Now, in our train function, we begin by setting up our experiment. We create our CartPole environment. We then define the lists of hyperparameters for our 3 different reservoirs. Notice that the leaky rates are different, 0.2, 0.3, and 0.4. This is how we're creating reservoirs that capture information at different timescales. We then instantiate our multi-scale ESN with these parameters and wrap it inside our policy network. Finally, we create our Atom optimizer. And again, it's crucial to remember that when we call policy.parameters, the only trainable weights it will find are those in the single readout layer of our multi-scale ESN. The vast majority of our network's parameters are fixed, which is why this approach is so efficient. Now we're inside the main training for loop, which iterates through episodes. Each episode is one full attempt by our agent to balance the pole. Inside the while not done loop, the agent lives its life step by step until the pole falls over. At each step, it performs a sequence of actions. First, it passes the current state of the environment to our policy network to get action probabilities. Second, it creates a categorical probability distribution from these probabilities and samples an action. This is a key concept in policy-based reinforcement learning. Instead of always choosing the action with the highest probability, which would be exploiting its current knowledge, sampling allows the agent to explore by occasionally trying out less likely actions. This is how it discovers new and better strategies. Third, we calculate and store the log prob or log probability of the action we just chose. We need this later for the policy gradient update. Fourth, we execute that action in the environment, and it gives us back the next state, the reward for that step, and whether the episode is done. Finally, we store the reward we received in our rewards list and update our state variable for the next iteration of the loop. We're essentially just collecting data during this phase, a history of actions taken, their log probabilities, and the rewards received. Once the episode is over, it's time for our agent to learn. We use a classic policy gradient algorithm called reinforce. The first thing we need to do is figure out how good each step of the episode actually was. Just looking at the immediate reward of +1 isn't enough. We want to know which actions led to long-term success. To do this, we calculate the discounted return for each step. We loop through the rewards list backwards. For each step, we define its return R as its immediate reward R plus gamma times the return of the next step. This gamma is a discount factor, usually around 0.99, which makes future rewards slightly less valuable than immediate ones. This process gives us a much better estimate of the true long-term value of each action we took. Next, we standardize these returns by subtracting their mean and dividing by their standard deviation. This is a crucial trick that helps stabilize training by keeping the values in a predictable range. Now we calculate our loss. The formula is the heart of the reinforce algorithm. For each step, we take the log prob of the action we took and multiply it by the standardized return for that step. The negative sign is there because optimizers work by minimizing loss. By minimizing this value, we are effectively pushing up the probability of actions that led to high returns and pushing down the probability of actions that led to low returns. Finally, we perform our standard PyTorch optimization. We zero the gradients, backpropagate our loss, and step the optimizer. This sends the learning signal back and updates the only trainable part of our model, the readout layer. So let's take a moment to recap the advanced and fascinating system we've built today. We didn't just build a neural network. We built an echo-state network from the ground up. We went through the detailed theory and code for creating a sparse, random reservoir and ensuring its stability through spectral radius scaling. We then took it a step further, creating a multi-scale architecture by combining a team of ESNs, each tuned to a different time scale using a different leaky rate. This allowed our agent to process both long-term trends and short-term events simultaneously. We embedded this complex brain into a reinforcement learning agent and successfully trained it using the reinforced policy gradient algorithm, teaching its simple readout layer how to interpret the rich dynamics of the reservoirs to solve the CartPole problem. The result is a highly efficient recurrent model that demonstrates a powerful alternative to traditional RNNs. I highly encourage you to take this code and experiment. See for yourself how changing the reservoir sizes or the leaky rates affects the agent's learning speed and final performance. Try applying this architecture to a more challenging environment. This is a fantastic foundation for exploring the world of reservoir computing. Thank you so much for joining me for this deep dive. If you enjoyed it and learned something valuable, please give the video a like and subscribe for more advanced AI tutorials. Happy coding!